Time to start our third talk today. Our third speaker is Wojciech Chachólski from KTH Stockholm, and the title of his today's talk is Enabling a Machine to Sense Geometry. Wojciech, the screen is yours.
Thank you. Thank you for the invitation. I'm speaking here on behalf of the entire TDA group at KTH. Okay, here are the people. So in my talk, I will give you a suggestion of how one can give a machine a sense which is sensitive to aspects of objects that we ourselves might consider geometric. So I could go quickly through basic definitions and go directly to examples and illustrations. But I would like to give you, place this machinery in some context that, it has been important for me, and I think it might be illuminating. Okay. So what is a sense? There are two ingredients. We need a technical apparatus. In this case, it will be based on homology. But, essential aspect of this apparatus should be that we can adopt it and train to different circumstances. We are born with the same apparatus to detect smells, but depending on where we live, we develop it based on our experience and needs, right? So imagine that we have performed some experiments and collected measurements and organized these results in a collection of objects representing these experiments. I call this representing a set of objects U. Okay. For example, you might have done some persistent analysis, and these objects could be parametrized vector spaces, maybe even multi-parameter parametrized vector space. So these objects that you used to represent, these objects represent points in possibly a very strange universe of, for example, RNA expression levels or some complicated tests performed on industrial products. So we find ourselves with a rather unknown universe. So what is it that we do first if you find yourself in an unknown place? Well, you need to be able to compare these objects, okay? And that you can do via means of distances. So we need to look for distances between these objects, okay? But it is important that a choice of a distance should depend on the experiment and not on the numerical values constituting these representing objects. For example, genetic readings might lead to some barcodes, and by some just sheer coincidence, similar barcodes are obtained from testing some industrial products. It should not be surprising that there might be some distances on these representing objects which are more suitable for this genetic data, and some other distances which are more suitable for data representing some test of industrial products. Okay, so we should not just stick to bottlenecks or Wasserstein distances on persistent modules. The choice of these distances should depend on the experiments. Okay. So, all right, you choose such a distance, possibly talking with a data provider, with biologist or a person from a company of industrial production. Okay. So how can you use it to analyze data? And at the end of the day, we want to analyze the information we got. Okay. So that means that you need to be able to use statistics, machine intelligence, maybe in form of some machine learning algorithms, which means that we need to choose kernels on these representing objects U. Okay, the kernels that which, for example, allow us to apply various machine learning algorithms. Okay, so for that purpose, we need to choose an observable, which is a function from U. Assign a number your representing object, to every representing object. Okay, and this should be very simple functions. This is you find yourself in an unknown universe, so you try to observe the objects you are in, so you assign some very simple values, maybe number of clusters, maybe the dimension of vector spaces, or rank of some modules, etc. Very simple, observable. Okay. So, for example, in the case of, it could be, by the way, it could be discrete, right? It could be just sort of natural numbers as values. So, for example, in the case of these parameterized vector spaces, we might take the rank. What is the rank? Just to remind you, the rank is the smallest number, for which there is a surjection from a free module onto X, the minimal number of generators of X. That's like the simplest thing that you might consider. That's the simplest of observable, the smallest number of generators. Very easy invariant to calculate, for example. It's a linear time. All right. Remember that we are in this unknown universe, so we should have these sort of simple invariants, counting invariants. Okay. So now what do you do? Okay, you have the distance, you have an observable. So how can we analyze our data? Well, because we chose a distance for any representing object, we can consider disks around these objects, because we chose a distance. And now what we can do, we can associate with this object a function. So a little bit, not a number as R assigns to X, but a function. Okay, and here is a definition of the function. What you do, you look at X, you look at these disks of various radius, and what you do, you want to minimize the invariant, the observable on this disk. Okay. So, for example, so this function X, if S is less than T, it's a smaller radius. Then, of course, you minimize over the smaller disk. The function is non-increasing. Okay. Is non-increasing. All right. So we call this assignment, which assigns to an element, to a representing object, this function. We called it a hierarchical stabilization of R. Okay. So we use the geometry. Induced by this distance on U to define, to represent these representing objects by functions. Okay. Now we call it hierarchical stabilization because this function is continuous. Continuous, where where in U you endow U with a metric D, and you can endow this space of functions with LP distance. So we consider like integrable functions or Lebesgue integrable functions. It's always continuous. Okay. So we can think about this as that every distance on U, every choice of comparing objects on U gives us a kernel on U. We can think about this as a kernel if we, for example, choose the L2 distance. We think about this as a Hilbert space. Okay. In this way, so a choice of a distance help us in representing these representing objects as elements in some Hilbert space, in which there's lots of analysis, lots of probability developed in this work. Okay. All right. So this is the way I propose to study to use distances in order to study these representing objects. Okay? We extract something simple that we can compare, etc. Do analysis. So, for example, if we choose a distance on these parametrized vector spaces that TDA people like a lot, we can consider these simple observables, which is the rank, the minimal number of generators, and we can form the hierarchical stabilization of that invariant, and the obtained kernel is called the stable rank. Okay. So, all right. So again, I can simplify I can represent these parameterized vector spaces by these functions, and each such representation depend on a distance. So now I have to tell you next step, I have to tell you, how to construct such distances. Okay. So the most generic way I know of constructing, well, quite specific distances is via noise systems. We worked here at our group for quite a while. Eventually it was published in 2017. So what is a noise system? Noise system is a abstraction of what you might consider a disks around the zero object. So you think about this, you think about this S epsilon as a disk of radius epsilon about the zero object. And it is an abstraction of what these disks should satisfy. So for example, this is a disk around zero, so it has to contain zero, okay? Another thing, of course, if radius epsilon is less than tau, then the disk with radius epsilon has to be included in the disk with radius tau. And here's an algebraic constraint. If you have an exact sequence of these parameterized modules, and if this bigger one is small, is of distance epsilon to the zero object, then so is any of its submodule and quotient. Okay. However, if x is epsilon close to zero and z is tau close to zero, then y can jump out, but not too far. It is in the disk with radius epsilon plus tau. Okay. So I'm just putting some conditions, algebraic conditions, on requirements on my system of disk around zero. Having such a norm, you can think about this as sort of a norm. There are standard ways of extending it to a distance for all tame parameterized vector spaces. Here's the usual one. You compare not x and y not directly, but through a third object via various maps, and then you see how big, you evaluate how big the kernels and co-kernels are, you sum them up, and you optimize. You try to compare x and y, so this becomes the smallest. Okay, this is a standard way. This defines you a distance, satisfies triangle inequality, etc. So a noise system leads to a distance. Now, amongst noise systems, there are very specific, there are a little bit, noise systems are quite general. So among them, they are a little bit more specific. A noise system is called simple. So these neighborhoods, these disks around zero, we call it simple if the following happens. It is closed under direct sums. So imagine you have barcodes, bunch of short barcodes and other short barcodes. You stack them together and you ask, do I consider this module still small? Okay, you have lots of barcodes, but short ones. Do you still consider this as small? Okay, that's a choice. If this happens in your choice, then that's one of the requirements for the noise system to be simple, to be closed under direct sum. Now, what is this condition equivalent to? It is equivalent to the following condition. Remember, we want to minimize, for this hierarchical stabilization, we want to minimize certain things. So here, let's minimize in a little bit more direct way. You start with this x and you look at the submodules for which the quotient is small. Okay, so such modules form a poset, and you might ask, does this poset contain a minimal element? Can I find the most efficient way, or maybe there are several minimal elements, like an efficient way of minimizing of making the quotient the smallest. So the existence I do not know, but the condition A, being closed under direct sums, is equivalent to saying that if such minimal element exists, then it has to be unique. Condition A is equivalent to the uniqueness of minimal element in this poset. Okay, so, but it doesn't guarantee existence. So for simple noise systems, you have to sort of give it, that's the axis, assume that it has a minimal element, which has to be unique by condition A. Okay, and we call this submodule epsilon shift and denote this in this way: x square bracket epsilon. Right. So here's the third condition, the last condition, and it might look technical, but it's quite essential. What it means that this shift does not increase the number of generators, minimal number of generators. The rank of this shift is at most the rank of original object X. Now, what this condition, it's this technical condition, says that simple noise systems are intimately related to the rank, to this observable, to this very simple observable. Okay, simple noise systems are connected to the rank. That's what I would like you to remember. Of course, this condition is invisible if you take one parameter persistence, because rank is monotonic function for one persistent. Okay, but it's somehow invisible. To see the role of the rank, you need to sort of look for this multi-parameter persistent. But that's what I would like you to remember. So the theorem is that if D is a distance associated with a simple noise system, you remember I defined this kernel, this stable rank kernel, which minimizes over this rank over various disks around X. Now, remember, such disks may be infinite. So, if I even minimizing over an infinite subset can be, a very hard problem. It may not be algorithmic problem, all right? It may not be, but for this particular invariant and for a noise system, which is simple, the theorem states that this stable rank can be calculated by performing finely many calculations. Okay. I do not know whether that's true for arbitrary noise systems. It has to be simple, and it has to be this rank environment. Here's what I want to sort of mention. If you would like to study, for example, the 2-parameter persistence or 3-parameter persistence, if you want to study other invariants such as higher syzygies, higher Betti numbers, Hilbert polynomials, you probably need to look for other noise systems than simple ones. I will come back to it in a second. Simple noise system is something that most of you actually have seen. Okay, this is because there's a theorem that says that there is an isomorphism between spaces of simple noise systems. These noise systems that I gave an algebraic characterization of, this space is isomorphic to the space of contours. And what is a contour? A contour is simply an action or a lax action, okay, of this additive monoid from real numbers from 0 to infinity on the poset of n tuples of non-negative real numbers. So what does it mean? That's an action. It's a lax action. Well, it has to be act on a poset, so it preserves these inequalities. Okay. Well, if you act by 0 on V, you might get V or something bigger because of lax. But for the purpose of this talk, you just assume that's an action, so it's equality. And then if you act by A and then you act by B, then it should be the same as acting by A plus B, or it doesn't jump over. Okay, because of laxness, but you can assume that here are the equality. We're not going to look for other examples. Okay, so here's an example of a lax action, just a translation by some, in the direction of the diagonal, for example. That's just a, translation is a nice action. We call this action standard. Okay. So contours have been such actions have been around for quite a while. In TDA community, for example, Bubenik, De Silva, and Scott call them superlinear families, and they use them. They sort of use them with interleavings. That's from their work. Interleavings and contours are sort of the same. What I just told you that these contours and hence interleaving distances are the same as simple noise systems. which I gave you, algebraic characterization of, okay? But what I also told you that these simple noise systems are, intimately related to the rank invariant, to the simplest invariant, which means that, for example, if you want to study higher syzygies or beta 2 or beta 3 in multi-parameter persistence, using interleaving distances is probably not a good idea. Okay, interleaving distances are intimately related to this, the simplest invariant you have of the rank. Okay, on the parameterized vector space. All right, so let's just simplify. Let's because I want to show you, illustrate some calculations. Let's just consider one persistence. Let's just reduce everything to one parameter. Okay, so how would you, if I ask you, give me one persistence, give me an action. How would give me an action of give me an action of you want to act by the monoid of non-negative reals on non-negative reals, on the poset of non-negative reals. How would you actually come up with such an action? Okay, so here's the easiest way that I know of. You choose a function with positive values, integrable, and what you do, probably easiest would be if I just draw a picture. Okay, so here is a function, integrable function, that's f, and you start with element v, and you want to act on this by element a. So question is, I would like to, how far do I move along this? So you move, so this area is A. You move as far, to the point where this area becomes A. This is an action. Okay, this is actually an honest action. Okay. So what it tells you that every such density gives you a contour, which is the same as simple noise systems, which gives me a distance. So I just give you a rich space of distances on parameterized vector spaces, one parameterized vector spaces. Every such density leads to a distance. Okay, which means that I have this really rich space of distances. Okay, or in other words, each such function, each such density leads to a kernel, leads to a representation of these parameterized vector spaces into this Hilbert space. And every distance, every such function leads to a different representation. Okay. So in order to find an appropriate representation for your particular data analysis task, you might search through an appropriate function. All right. So I just told you that each function leads to a kernel. So this turns out to be you can characterize these same parameterized vector spaces in this way. If you have two parameterized vector spaces, they are isomorphic if and only if these stable ranks, these representing functions, are equal for every density. All right. So, but remember, tame parameterized vector spaces, those are just, they can be decomposed into barcodes. Those are just barcodes, which means that this rank, is as difficult to calculate as the barcode itself. But I was very, very careful in this talk not to mention barcode before. You see, I'm very, very careful. Barcodes, of course, existing software, like we use Ripser, a great software, can be used for calculation purposes. But we believe that the stable rank, which is, at the end is the same as barcodes because they are determined by X. Okay. It is about the geometry of this, what we do, we put a distance, maybe different distances, but we choose some distance on parameterized vector spaces. And these invariants, this representing we typically represent a parameterized vector space barcodes. Here I propose to representing them by these stable ranks. But the idea for the stable ranks that you can sort of recover barcode from as well, is about understanding the geometry of these parameterized vector spaces and how various objects fit in this, in this space based on the chosen distance. Okay, it is not about indecomposable. It is about the geometry of these parameterized vector spaces and the way how we retrieve that information from, some choice of geometry, for example, by choosing a distance here. Okay. All right. All right. So that's a context that I would like to tell. I wanted to tell you about these stable ranks. Okay, which at the end, with one parameter, they can be translated back and forth between barcodes, etc. Okay, so let me give you one. I will give you two. This is the first one. How I can enable, give a certain sense to machine, and just wonder what this sense might sense. Okay, so. All right, so I give you two components. I need to tell you, describe technical apparatus and ability, and then explain what is the ability to adopt to train it. Okay, so let's consider point cloud. That's an object that we probably might feel we can recognize some geometry there. Okay, what is my technical apparatus? So I take the homologies of the Vietoris-Rips complex associated with, let's say we chose Euclidean distance, or some other distance actually on B, but Euclidean, let's say. And we take, H0 or H1 or some other homology. So this is parameterized vector spaces, okay? I choose a distance on these parameterized vector spaces. And for example, given by a density, right? Given by a density. And then I consider the stable rank kernel, okay? And then I represent my point cloud by this function, right? So I enable the machine, you give a machine this point cloud, and and gets its sense, signal this function, okay? This function. Now, how am I going? How can I learn? How can one machine be better at detecting certain things than other? The training is to look for D for which this stable rank kernel discriminates better. Okay, that's what would be sort of learning. Maybe in that environment, that D, when my point cloud is represents some biological information. Maybe this particular distance is better for that purpose than other distance. Okay, so so I wonder, So now the question, I give you a sense, what does this sense do? Okay, what is it sensitive to? So let's just play around. Let's generate 4 types of plane figures that I will label circle, rectangle, triangle, and a path. You might imagine why the names comes from. I will show you an example. I will generate 500 of each, resulting in data sets of 2,000 elements. Okay, 500 of circles, 500 rectangles, triangles, and path. Okay. For each element in this data set, I will extract, according to my apparatus, H0 stable rank with the standard contour. Okay, so I'm not changing standard contours. This is related to the usual bottleneck. Okay, distance. So here's, for example, of 4 elements in my data set. Here's some, I typically generate with a little bit, noise, normal noise, a little bit normal noise around the circle, rectangle, triangle. And here are these representing functions, representing, kernel, elements of this standard contour kernel. Okay. So we split this data into 70% and 30%. Training and test. I fit SVM to this training, okay, using this standard stable rank kernel, and we evaluate on the test set. We repeat the whole 20 times just to sort of see and record accuracy, and achieved average classification accuracy is 35%. Okay? Like if you were randomly choosing, it would be 25%. Okay, not very impressive. But let's change my apparatus. Let's, instead of H0, you might sort of suspect that maybe H0 is not so informative. Let's do H1, okay? Let's do H1. We do the same procedure, except that we take H1 stable rank with the standard contour. Okay, the same procedure, okay? The average accuracy becomes suddenly 88.5%, okay? So we know that, okay, H1 is, you know, that geometrical sense, you know, it's a little bit better. But let's change the density. Let's, you know, imagine that this, you know, this computer, this machine evolves, you know, and it tries to sort of get better at detecting these shapes. So at the end, he says, like, I would like to measure, you know, the distance between you know, these, you know, I'm choosing that density, okay, that density. And we repeat this whole procedure with H1 stable rank, however, with this new contour, okay, with this new way of measuring parameterized vector spaces, and achieved average accuracy becomes 95%. Okay, that's actually considerable this difference. Okay. One can do similar. I will not do it now. I can do similar experiments using, for example, random point processes, and one might sort of consider, you know, do I see a difference between, you know, I can have some point processes on the unit square generated by different distributions, and you might sort of ask whether this apparatus distinguish between, you know, geometry of various distribution of point processes on the unit square. You know, here we have you know, we have some geometrical intuition behind the shapes. For point processes, it's a little bit harder, but this works quite well, actually. This works actually quite well. But I would like to enable my machine with another sense. So again, we consider point cloud, because that's somehow, so let's say, geometry, that we have some intuition behind geometry. And my technical apparatus will consist of the following. All right. I will choose a number, k. Now I will consider a family of subsets of size k. I might choose them randomly. I could take all possible subsets of size k. All right. Now, what I will do for each of the subset in my family, I will now take the Vittori-Rips complexes of these subsets. Okay. So, for example, if you take k equal 10, these you take the, you know, homology of 10-point spaces. This is very fast to calculate. It's parallelizable. Okay, because you can do it, you know, at the same time for different subsets. Okay, of course, if you take too many subsets, then, you know, you have to do that might be a problem. But, you know, and now, you know, we choose a distance on these parameterized vector spaces, given, for example, by a density. And now we will represent our data, or our D, not by the homology of the Vittori-Rips of the global space, but by the average, you know, stable, you know, I will take this homology of these subsets. I can take a stable rank that, you know, this lies in the Hilbert space, so I can take these averages. I can add functions and take the average. Okay. So that's how I will represent my data D. Okay. So here's my interpretation of this. First of all, you know, if you have some data D, why would you, I mean, of course, we can represent this globally. We can look at all distances between these points, but maybe equally efficient or better is to look at all possible subsets of 10 points and only consider distances between these 10 points. And maybe, you know, this collection of all these 10 subsets will tell us quite a bit about original space. Maybe this global, we don't need to know all the distances. You know, if you calculate distances, you know, if you encode my space of maybe 1,000 points by its subsets of 10 points, you recover quite a lot of information. Okay? And then you take this average. Okay, that's a technical apparatus. So now, how would you train this? Well, you will look for K and you look for D, for which the average stable rank discriminates better. That's what you'll do. So because last time I showed how to choose D, now let's look for various Ks. Okay, for example, if K is the number of elements of D, you don't get anything. Okay. All right. So again, I will generate 4 types of plane figures with the same labels as before: triangle, rectangle, whatever it was for path. But this time, however, I will add 30% of ambient noise. Right? I will add 30% of ambient noise. For example, okay, I will generate 30%. Those are, I think, 200 points, each of them, of these pictures. 30% is kind of randomly, I think, uniformly distributed, and the rest is taken with a little bit normal noise from the figures. 30% of ambient noise. Now, for each element in this data set, extract averaged H1. So use this apparatus I described before. Stable rank. With K, it's 20%. So in this case, it's 40. Okay, 40 because it's 200. And D, the standard contour. Let's don't vary D here. Okay. So split data as before, 70-30. Fit SVM. Okay, using the standard stable rank kernel. Okay. Repeat the whole procedure 20 times. And I wonder, I should sort of make a poll, what do you think average accuracy will be? I added 30% of noise. Okay. The average classification accuracy is 86%. It's very, very high. Okay. In fact, here's if you start adding noise, perform the same experiment, but you start adding the noise. That's the x-axis. Okay, what's the percentage of the noise? Look, if you add 40%, and if you use this is without subsampling, use the original the sense number 1, you get 40, you get around 50% accuracy. But if you allow this sense 2 to do this, you still get above 80% accuracy, even with 40% of ambient noise. Okay? Even with 40% of ambient noise. All right. Similar things you can ask lots of interesting geometry. For example, I can give you like a noisy circle, like you have here, and then you choose a point, and you might ask, is that point inside the circle or outside the circle? This sense is very good at detecting whether a point lies inside or outside. I'm not defining, here, in the sense what is, I'm not defining to machine what a circle or triangle is. The sense will see a difference between those 4 shapes. In the same way, if you take a point, and I didn't prepare this, my time is soon finishing. If you take a point inside, outside, this apparatus is very good at detecting this. And same thing for triangles or a square. Okay. But here's another example. This is a data collaboration with Joana Pereira from Karolinska in Stockholm. So data was correlation networks extracted from resting state MRI images of medicated Alzheimer patients, not medicated Alzheimer patients, and controls. Okay. So typically this would be like a matrix. However, it's not symmetric of correlations. So there was lots of sort of guessing and math. How do we transform that information into something that sort of our sense can sense? But we took this sense number 2, averaged H1, based on H1 stable ranks, and here's the result. Yellow is medicated Alzheimer patients, red is not medicated, and blue are controls. And you can see that there's a big number. There's a big subgroup of Alzheimer patients that has the sense the geometry of these correlation networks of these patients is considerably different than the geometry of the networks of some other patients and control. Okay. And I think this is 40 minutes, right? Thank you so much for your attention.
Thank you, Wojciech, for an interesting talk. So we have now time for questions. We use the same procedure as before, so please put your cues into the chat window. Before some cues appear, I wanted to clarify. You mentioned that you have to add this assumption about the existence of the minimal element in simple noise systems. So in practical terms, I guess it doesn't matter. Am I right? Or you still see situations where it may matter?
No, so yeah, so I mean, sometimes you see, sometimes I do not know whether if I want many short bars to be still regarded as noise, right? as small. For example, sometimes maybe you want, so we see more and more recurrence of the situations in which we can use the number of short bars as a distinguishing thing. So that depends on what you want. The trouble is if you do not assume that, suddenly calculations becomes much harder. So you see, this theorem, where was it? Sorry. This theorem this theorem that that I can make this calculation, that this stable rank stabilization only requires finally many calculations. I know only for simple noise systems, I do not know. This is typically a bottleneck for the thing. So if you do not assume that, suddenly you may not have got.
Oh, okay, and the noise I hope disappeared. So I see now questions. So Patrizia.
Yes, I liked so much your talk and your approach, and particularly your decision to focus on choosing different distances according to the experiments. And you spoke about observables. Do you have any ideas, suggestions about how we could choose observables in applications?
Right. So look, right now, the only observables that I know, okay, if you represent your objects by parameterized vector spaces, the only observables that that we have, that I have guarantee, for example, that's algorithmic. It's a rank. What's interesting is that if you look, for example, for the highest syzygy, it's also rank for one persistence is monotonic, which means that if X is a submodule in Y, that the rank of X cannot be bigger than the rank of Y. Now, if you take for two parameter persistence, this is not the case. A submodule can have a huge rank. There are huge rank submodules of a free module with the one. But there is the highest syzygy is monotonic. So the highest syzygy. If X is a submodule of Y, then the highest syzygy of X cannot be bigger than the higher syzygy of Y. So highest syzygy seems to be this invariant that somehow is more related to the rank from one persistence, to like barcoding for one persistence, the highest syzygies. The trouble is that I do not know a noise system or a distance for which I can calculate stabilization of the highest rank. It could be that, you see, because when I sort of told you this hierarchical stabilization, right, this works, it has nothing to do with parameterized vector spaces. So it could be that I could represent you by some other things like graphs. And maybe these graphs has better observable. You can do the same thing. This works in full generality. There's nothing assumption about parameterized vector spaces. So you might represent your objects by graphs, on which the space of graphs, or you have and then try to find distances on these graphs, and then try to maybe find some invariants, they're observables that are sort of whose hierarchical stabilization is calculable. Remember that so important thing about hierarchical stabilization is that it is stable, it's continuous. That's the whole thing. So you convert something presumably totally incontinuous, it could be discrete, into something continuous.
Thank you.
But for parameterized vector spaces right now, we work very hard to get what is for the highest syzygy, because it has, but somehow I have impression, so it cannot be like interleaving. Interleavings are related to the rank. If you talk about interleavings, it is really related to the rank, and this is it. Okay. So for higher syzygy, you should look for something different than interleaving, and that and that's hard.
Okay, so there is also a question from Claudia.
Thank you very much for the very inspiring talk, Wojciech. I have two questions, maybe related, maybe not. How do you navigate the space of distances in order to find the best one?
Right, so, okay.
That's the first one. And the second one regards to the fact that if you are told by experts or by common people what are the distances between two objects, they could choose some measurements that have not the properties of a distance in mathematical sense, but are more similarities or something like that. Can you foresee that some axioms of distances can be forgotten in this approach?
Right. So yeah, let me yes, here I wanted to do this. So okay, so the way we do this. So first of all, what we do, the distances, so I don't know how to search for distances, but I know how to search through such functions, and I know that these functions lie in these distances. So very often what happens is in our examples that we search not this entire distance, space of distance, but we search through the space of these functions. Now, of course, I would like to make it do it automatically, use a machine to do this. Maybe I would like to evaluate. I would like to be able to evaluate that function is better than the other, and then go in the direction of the gradient of that function. Okay, that we still do not know how to do right now. The way we search through it is like in this example. The way we search through it, we just sort of have a sort of random search for piecewise constant functions, and then choose. We apply this machinery and then choose the one that somehow increases. What's interesting is that sometimes there is no one distance. In fact, we have quite efficient ways of you choose 2 or 3 distance, and then you represent your data by 3 functions, each of them given by different distances. And these 3 functions have much better, we have circumstances in which, having, 2 distances or 3 distances is more efficient at distinguishing than just, saying like, well, that's the distance that I should use, okay? But again, right now, we don't have a good function that we would like to minimize over these space of functions, okay? That is somehow, that we do not have for now, that you can sort of try to look at the gradient. And what was the second question?
Yeah, and
Oh,
now
right, about the
if
distance, a
your
triangle.
distances come from these contours, then I guess you always get a distance. But if you, for example, have a data set of images and asks to people for similarity and they give a vote, so maybe the metrics of similarities you get is not
Right.
not a distance.
Yeah. So my question. So yeah. So I can't remember from top of my head. You know, if when we do this hierarchical stabilization, this one. If we do this hierarchical, this one. Sorry. So if we do this hierarchical stabilization, so you know, so whether one needs, whether one needs this distance d on u. So I think you can go away with a lot of much less than d, for example, satisfying triangle inequality. Okay. The trouble is that then, you know, the question, you know, the way you prove that theorem, okay, the way you prove that theorem is that you show its Lipschitzness. And sometimes, you know, no, not continuity, of course, but Lipschitzness. And for that, there is a room for not requiring all these, you know, like triangle inequality, for example. Okay.
Thank you. Thank you. Very interesting. Thank you again.
Okay, I do not see more questions and we are already out of time. So let's thank Wojciech again.